Okay, now I would like to explain the result part. The percentage of hemolysis for supernatants can be calculated by using the formula below. The percentage of hemolysis equals to absorbency of supernatant over absorbency of supernatant from the tube treated with distilled water times 100%. And for section A1, different types of solutions are being used, and hypertonic solution has the lowest absorbency of supernatant, which is 0.009, and thus the percentage of hemolysis for this solution is also the lowest, which is 0.73%. And for hypotonic solution, the absorbency of supernatant is the highest, which is 0.955, and the percentage of hemolysis for the hypotonic solution is 77.45%. And we can also observe that for the hypertonic solutions and isotonic solution, at the end of the experiment, clear solutions and will obtain while the red precipitates will appear. While for hypotonic solution and the distilled water, which act as the control tube, red solutions is obtained. And for sections A2, different concentrations of NaCl solutions are being used, and 1% of NaCl solution has the lowest absorbency of supernatant, which is 0.006, and the percentage of hemolysis for it is also the lowest, which is 0.49%, while the absorbency of 0.2% of NaCl is the highest, which is 1.014, while the percentage of hemolysis for this solution is also the highest, which is 82.24. And we can also observe that from 0.5% of NaCl to 1% of NaCl solution, colorless solutions will obtain at the end of experiment, while for 0.45% of NaCl, the solutions will turn pale yellow, while for 0.4% of NaCl, the solution will turn pale orange, while for the control tube, and from 0.1% to 0.35% of NaCl solution, the solution turns to red color at the end of experiment. And from the graph of the percentage of hemolysis against the NaCl concentrations, we can observe that there is a downward trend in percentage of hemolysis when the NaCl concentration increased. And we can also observe that at 0.75% of NaCl solution, the graph start to flatten up. This proves that 0.75% of NaCl solution is isotonic to the red blood cell. And for sections B, also different types of solutions are being used, and we can observe that 150 milliosmol of urea has the highest absorbency of supernatant, which is 1.135, while the percentage of hemolysis is 95.7%. While for the 300 milliosmol of urea in 300 milliosmol of NaCl, the absorbency of supernatant is the lowest, which is 0.008, while the percentage of hemolysis for this solution is also the lowest, which is 0.65. And we can also observe that for 300 milliosmol of sucrose, glucose, and NaCl solutions, and 300 milliosmol of urea in 300 milliosmol of NaCl solutions, the solution turns colorless at the end of experiment. And for 300 milliosmol of urea, 150 milliosmol of urea, 600 milliosmol of urea, and the control tube, the solution turns red at the end of experiment.
The objective for this section was to determine the reference value of the absorbency A and the color of the RBC in three types of solution, which are hypertonic solution, hypotonic solution, and isotonic solution. From the result, it was found that the supernatant of both hypertonic and isotonic solution remained clear, while for the hypotonic and control, the supernatant were red in color. This was due to the increase in the membrane permeability of hemoglobin of RBC in these solutions, causing the red hemoglobin pigment lost from the RBC into the solution and turning the supernatant into the red color. Since the chlorination of the RBC occurred in the hypertonic solution and there was no change in the cell's volume of the RBC in the isotonic solutions, Hence, there will not be any loss of hemoglobin from the cells. So from the previous table, you can see that there was only a small percentage of the hemolysis of RBC occur in this both solution. It was also important to note that the percentage of the hemolysis of RBC in an isotonic solution was higher than that in the hypertonic solutions.
In section A2, the serum concentration of sodium chloride is used to determine the relationship between the concentration of sodium chloride and the percentage of hemolysis. Based on the theory, the percentage of hemolysis is inversely proportional to the concentration of sodium chloride. When the concentration of sodium chloride increases, the amount of water entering the cell decreases and thus lowering the percentage of hemolysis. Our isotonic point is 0.75% of sodium chloride, which is slightly different with the theoretical value 0.9%. In isotonic point, there is no net movement of water in or outside of the cell. Therefore, the cell remains in its original shape and the hemoglobin stay in the cell.
Well, when the concentration of sodium chloride is less than 0.75%, it is hypotonic to the intercellular fluid of erythrocyte. Hence, it will swell and some even lyses, causes the hemoglobin to diffuse out from the pore of erythrocyte and hence the tense tube turns red. When the concentration of sodium chloride is more than 0.75%, it is hypertonic to the intercellular fluid of erythrocyte. Hence, water diffuses out from erythrocytes to dilute the concentration of sodium. So the cell will shrink and decrease in volume. And the color of test tube remains colorless.
Here are discussion for section B for the 4 other test tube, which is 300 milliosmol of sucrose, 300 milliosmol of glucose, 300 milliosmol of NaCl, and lastly 300 milliosmol of urea in 300 milliosmol in NaCl. Observations show after we centrifuge it, the colorless for the all 4 solution. Colorless means red blood cell does not burst. The hemoglobin is still in red blood cell. That's why the color is maintained colorless. The condition for this to happen is whether the red blood cell clinate or red blood cell in isotonic solution. When it clinate, it means the solution are in hypertonic. But for our cases, since the percentage is almost equal to 0, the condition is isotonic, which means rate of water diffusion between ICF, intracellular fluid, and ECF, extracellular fluid, is almost equal. No change in cell shape, no crenation, and no cell rupture.
I'm going to discuss the result of part B. If you can see here, there's 3 test tubes which contain all urea, but in different concentration. So after we centrifuge all of these, the result shows that the percentage of hemolysis C shows highest, which is 150 milliosmol urea, followed by B, which is 300 milliosmol urea, and followed by A, which is 600 milliosmol urea. C, which is 150 milliosmol urea, is highest because it is most hypotonic compared to A and B. For B, 300 milliosmol urea, initially it is isotonic to the red blood cell, but because of urea is a penetrating molecule, so the urea from ECF penetrate into ICF. It creates the ICF hypotonic to the ECF. Thus, all the red blood cells hemolyze. This also applied to A, which is 600 milliosmol urea. For A, 600 milliosmol urea, initially the ECF is hypertonic to the ICF, but because of the role of urea which is penetrating, thus the red blood cell can undergo hemolysis. If you can see here, the result shows after we centrifuge it, all the test tubes are red in color. This is because all the red blood cells undergo hemolysis, thus the mixture become red in color.
In conclusion, the percentage of hemolysis is inversely proportional to the concentration of sodium chloride. Osmolarity is determined by the total concentration of solute, regardless whether the solute is penetrating or not penetrating. And the last one, The movement of water molecules depends on the tonicity but not osmolality.